Hello everyone, my name is Berk Demirkan. I am a undergraduate student at Berk University, and this is going to be a video about my EE102 term project. So I chose to make a line follower for my term project. Why a line follower, you may ask? So it goes way back. When I was 9 or 10 years old, my big brother was studying at the Chankaya University. And there were these like big robot days where a lot of line followers, maze solvers, or like stair climbers used to compete against each other. And like my big brother used to take me to almost all of them. After seeing a lot of like robots and talking to a lot of developers of those robots, I grew quite fond of the robotic industry. Even then, I had made my research and wanted to compete against other competitors, but unfortunately couldn't due to certain family reasons. But now that I am in university, I have very limited freedom now, so I can choose to make whatever I like, and they will support me however they can. And I decided to test my theoretical knowledge and try to make a line follower using a basis tree FPGA board. So, however, my TA said that it needed a little bit more to be considered a term project because it seemed too easy. I added a color sensor option to the proposal, and it was accepted. However, later he said, during the phase two, he said that the color sensor didn't need to be there because it followed the line very, very well. So now let me show you a short clip of my robot. As you can see, it follows the line pretty well, and it slows down when it's over the red. So now I got my robot with me, and we're going to go over how exactly it works. So as you can see, there is a reflectance sensor array, a whole 16 of them, and they are all connected to the basis tree through the PMOD connectors. There is a color sensor which has its own LEDs to mitigate the uh, outside factors. There is a motor driver right here, which lets me control the DC motor speeds with PWM signals, which is very useful when controlling motors because the basis tree gives out 3.3 volts, and my motors need about 6 to 9 volts, and I'm currently powering them with 9 volt 6 AA batteries, as you can see. So now let's take a look at the code.
Uh, Here we are. We're in Vivado right now, where I coded this line follower. Uh, as you can see, the top module doesn't have many things in it. It basically does all the connections between the other modules and with the outside world as well. So uh, these are for setting the direction of the DC motors and to enable them with a switch, as you can see. This is for displaying the error on the 7-segment display. This this is for setting the LED of the color sensor as high so that it works all the time. So I'm using a 30 millisecond period clock to synchronize all of the processes that I'm doing. So the sensors are pulled every 30 seconds and the colors change every 30 milliseconds. If we take a look at the singular sensor module, we are setting the so I'm using enable signals with this. This is setup enable, count enable. So the setup sets the IO pin to high for 15 microseconds, and then it says IO line to high Z, which means it is in input mode. How my sensors work is that you set them to high for at least 10 microseconds and then measure the time it takes for the IO line to go low. And that time can indicate whether it is on a black surface or a white surface, basically. So here I am setting the pin to high for 15 microseconds and then counting. Because the values of the sensor is very unreliable, make some. Uh, I had to implement some functions like right here. What this does is if it's so the let's see, yeah, here we go. So it's 7. Okay. So if the sensor value is 1 for 7 clock cycles, then it sets the sensor value to 1, uh, output value to 1. If it's 0 for 7 cycles, then it sets it to 0. Otherwise, it doesn't change anything, as you can see. This is important because otherwise it sees white as black half of the time, and then yada yada yada. You can imagine how bad that is. Here we have the PID controller. As it's a very simple PID. So because the VHDL doesn't have support for floating point numbers and the base 3 doesn't have support for floating point numbers, I am using integers and then dividing it by 1,000, as you can see here, which means that like these are basically out of 1,000. So it has basically it's 1 out of 1,000. These each are. So uh, as you can see, my reference value is 7,500, which basically means the sensor is in the center spot. The as you can see, the proportional constant is 50, so 0.05, and the and the differential constant is 6,000, which is basically 6. Uh, and the integral constant is 0 because it doesn't really need to be anything else for a line follower because there's not much to do because there's not much for it to do, as you can see. I'm basically taking the uh, all layers sums and then the multi. So proportional is, as you can see, just the error itself and times the proportional constant. The derivative is the error minus the old error times the differential constant. And then the integral, as you can see, is the sum of all errors over time, and then the integral constant, which gives us as you can see, the output of the PID controller. This is a very basic PID because it doesn't really need to be anything else. These are things that I've used to use it as a like calibration module, basically. So I could calibrate the PID constants without reprogramming the basis tree, which really saved a lot of time. Here we have the motor control module. I have RGB inputs for the motor controller. Uh, these are seen as integers, but they basically are 8-bit values because they are between 0 and 255. Uh, uh, as you can see here, I am setting the base speed to 300 when the color sensor gives a red output. Otherwise, it's 600. Uh, I'm going to get to what these mean in else time. So as you can see, we are for the left motor we are uh, having the base speed and the PID output, and for the right motor uh, we are subtracting the PID output from the base speed. Of course, there is all like 0 and 1,000. There's all like the 0 and 1,000 things. As you can see, maximum speed. And the duties are straight up connected to the PWM controllers. So if you take a look at the PWM controllers, as you can see, it has a resolution of 1000. So the drift cycle is out of 1000, not out of 100. So these values basically mean these values basically mean like this value means 30% and this means 60% as you can see. Now if you take a look at the color sensor code, there's a lot going on here. However, it really isn't much. Uh, as you can see, I am using some. Where is it? So here is the my color sensor enables. This is the color counter, which basically increases as the thing goes up with the master clock. So it increases every 30 milliseconds at the moment, at least. It counts to 0, 1, and 2. 0 means red, 1 means green, and 2 means blue, basically. I have different counters for each of them, but these are all things that I've managed to create. They basically get the period of a square wave, of a the digital square wave, and the everything at every clock cycle it gets to a value, it gets to a different value, as you can see. To scale the colors from 0 to 255, uh, as as you can see, I have derived some formulas. So 255 times difference between that and then that. As you can see, I've gathered these constant values from. As you can see, I have derived these values from that. So I have I have gotten these values by just uh, getting the sensor up to a white surface and then a black surface. A white surface gives the minimum value and the black surface gives the maximum value. Mm, and then recorded all of those values and then put them all here. So then right now it works as a charm.
So that was all for my term project. I know I didn't do a great job at explaining, but hopefully you got some things correctly. Thank you for watching this video.